Morning, everyone. So we're going to continue with our final preparation in reviewing some of the main concepts that we learned in Unit 2. This Unit 2 here was a section on equilibrium. We actually found that this whole concept here sort of reared its head again in solubility. We looked at KSP equations. In acid-base, we started seeing Ka, Kb calculations. Pretty much the better you understand equilibrium in general, it did us good in the long run for the rest of the course. So, first thing, let's just define what is an equilibrium system. In chemistry, equilibrium is said to be dynamic. That word dynamic means things are continuing to occur. For dynamic equilibrium here, you need to mention two things. One is macroscopically, things stay constant. I want to emphasize here this is just constant in time. Outwardly, it doesn't look like anything is changing. So let's just look at chapter 3 here. Let's say a solubility equilibrium here. I have a solid, it's just sitting there. It doesn't look like anything is changing, and yet we know, because it's dynamic, microscopically, if you can really zoom in and actually see the particle level, you actually find that the reactions continue to occur. So how can these both be true? How can it be that outwardly it looks like nothing's happening, and yet we know, wait, things are actually dissolving, things are actually recrystallizing? Our conclusion was the fact here that the rates actually have to be equal. Right? Forward rate actually has to equal to the reverse rate. That will allow for both of these things here to be true. And in fact, part of Le Chatelier's statement is actually, if I have a system that currently isn't in equilibrium, all systems that are able to reach equilibrium, they're going to naturally proceed towards equilibrium, regardless whether you started off with pure reactants or pure products. For example, I could have started off with a beaker, I could have started off with just all solid, all reactants, let's say. Or I could have a mixture where I actually mixed in, here are sort of all ions, nothing has precipitated out, right? So this is all products. Reactions will naturally proceed towards an equilibrium system, and they're naturally going to continue forward rate equals reverse rate. Because we are always going to get a different temperature, right? At different temperature, we're going to actually have a different KEQ. We're going to actually have a new equilibrium, a new temperature. We're going to typically want to keep temperature constant. We do also want to have a closed system, because especially if one of the reactants or products, if one of them actually releases, let's say, a gas, I want to make sure that the gas stays in close vicinity, that they can actually do the opposite reaction and go back. If this were an open system, that gas there escapes, mass is completely lost, would never hit equilibrium. So that's why a closed system is very common in this section as well. So again, so for the first little while here, make sure you know that in chemistry, equilibrium is dynamic. Macroscopically, nothing changes in time. This is an important note here. The concentrations are generally not equal to each other. So sometimes people get in the hang of, yeah, equilibrium is balanced. Yeah, everything is equal. Let's think about the hockey game analogy. For your hockey game, I should have 3 forwards there. I can have 2 defensemen here. I can have any number of players on the bench, right? So when I say the reactant concentrations are generally not equal to products, well, I only have 5 skaters on the ice. I have maybe 20 players just waiting there. The 5 does not equal 20. And yet, throughout this hockey game, as long as my forward rate, as long as 3 go off and 3 come on at exactly the same speed, 2 go off for a line change and 2 come back onwards, as long as that rate is equal, we're going to always have a 5-player hockey game and the rest of the players on the ice. Different combination of players, that's fine, but generally the number of players on the ice don't have to equal the players on the bench. Okay? Once you hit equilibrium, they're not only equal to each other here, those rates there no longer change in time as well. So as we start looking at these graphs a little bit more, there were 2 types of graphs. Mainly, we dealt with graphs of concentration versus time and rate versus time. Let's say, for argument's sake here, we start off with all the players on the bench. All the players on the bench here is a really high concentration. All the players on the, well, there's no players on the ice, so it's 0. What's going to happen here is I'm going to steadily pull players off the bench here. The bench is going to lose people. The players on the ice are going to increase. Once these concentrations are equal in time, notice that they don't have to equal each other. Once the concentrations are sort of fixed, they might still be doing these line changes here, but as long as the line changes occur at the same rate, when these concentrations are constant in time, like we had mentioned here, we have hit an equilibrium. The rates, however, let's say the forward rate here are the players are actually jumping off the bench here, so we have the forward rate here. The forward rate is going to steadily drop because I'm going to lose number of players on the bench here. If the red here is the forward rate, the rates actually do have to end up equaling each other. Forward rate does have to actually match up to the reverse rate. And when these two things here are not only constant in time, when they're equal to each other, that also means we've actually hit equilibrium. So concentration just has to be same in time. They don't have to equal each other, but for rates, they have to be constant. Okay. So I've been saying here, yes, you can reach equilibrium from either reactants or products. Looking at a reaction, we want to decide, is this going to be an equilibrium system? Is it going to be a completion reaction, or is it going to be a 0% reaction? We had to look at two features to figure out the spontaneity. A spontaneous reaction just happens. The two features we want to look at was an energy argument. Energy was this endo-exo bit here. If nature had its way, nature always tends towards minimum enthalpy. I want to lower the enthalpy. The lower energy actually makes things more stable. There's less that can go wrong. Turns out for minimum enthalpy, it always favors the side that has the exothermic direction, has the heat term. Let's try an exothermic reaction. An exothermic reaction, A becomes B and heat. We have starting high, ending low. If I were on the reactant side, I want to go towards the exothermic side because that side has lower energy. That side is more stable. I point towards the heat term. What if it was an endothermic reaction? What if I had C plus energy? In an equation, it should always be plus. It should never be minus 10 joules or whatever. If I really wanted to be minus, I would just put the plus on the other side. For an endothermic reaction, I actually start low and end high. I do the hill this way. Well, if I were activated complex, if I were on the top, and I had my pick, either go to the left or the right, I'm going to prefer to go to the left because this side here is lower energy. Again, the exothermic direction is actually the side that has the heat term. That's going from the right side to the left side. That's exothermic. So if nature had its way and we could minimize enthalpy, point towards the heat term. We looked at the other concept here on entropy. Entropy was strangely enough defined as a disorder. Other words associated with this here is the amount of chaos in the system. It's the amount of randomness in the system. It's the amount of ways I can make my system messy. Entropy in general is a really hard concept to talk about, but we found that just looking at the state, we can actually predict whether it goes up or goes down. So entropy, we added order here. For solids, where particles are nicely arranged, not much energy just shaking in place, this one here has very low disorder. As you get to a liquid or a gas or somewhere in between, liquid or aqueous, and then a gas is definitely going to be the most entropic. As a gas, the particles are just sort of going every which way, right? Lots of chaos, lots of randomness here, so very high entropy. So in general, for entropy, what we looked for was not just having the most random phase, there was our order again, but also having the most particles. So let's take a look at an equilibrium system that we had, N2 and 3H2 becoming 2NH3. This reaction here is called the Haber process. It was an inexpensive way of actually using nitrogen in the air, combining it with hydrogen, and actually forming ammonia. In this case here, if I wanted to decide which side has higher entropy, first thing that you do is you look at which side has the most entropic phase. Well, it's gas all around. But this time, we actually have 4 moles of gas on the left side, and we only have 2 moles of gas on the right side. Even though gas is the most entropic phase, it is the most disorderly situation. Can you make more of a mess with 4 things or more of a mess with 2 things? Well, 4 things, right? If I have more particles. So in this case here, nature tends to unwind. Nature tends to become more chaotic. So in terms of entropy, we want to actually maximize entropy. So if I were doing this reaction here, if I wanted to know whether this reaction, does it actually hit equilibrium or not, I can actually point which way does minimum enthalpy point. Minimum enthalpy points towards the heat term. It wants to go to the far side. Which side does maximum entropy point? This time, maximum entropy actually points towards the reactant side. I want to become the 4 mole side because I can make more of a mess with 4 moles. In this case here, when there's competing features, I do want to go forwards because that side's more stable than me, but I sort of want to stay on this side because I'm more chaotic and more messy on this side. Anytime they compete against each other, they're going to end up in equilibrium. So that's the opposing tendencies. You might find a reaction where both of these features, if they both actually point minimum enthalpy, maximum entropy, if they both point forwards, well, there's no reason for me to stay on the reactant side. If I am 100% completion going one way, it actually is 0% going in the opposite way. Just be careful every now and then. Let me see if I can give you a question here. Let's take a solid plus 2B as a liquid, going forwards, becoming 3C as a gas. And then I'm going to put the heat term over here. right? They could ask you a particular direction. So we could answer our way. We could say, well, what does minimum enthalpy want to do? Minimum enthalpy wants to point towards the heat term as exo. What does maximum entropy want to do? Well, maximum entropy wants to go to the gaseous side. A gas is more entropic than either solid or liquid. So max entropy, both tendencies want to go forward. This one here would be 100% reaction. But what they could ask you for is they can ask you, what happens to the enthalpy and entropy for the reverse reaction? Now we can say, well, wait a second, right? We don't want to do reverse, right? But if they force a direction on you, you're forced to just answer their question. I know minimum enthalpy was going forwards. For the reverse reaction, if I'm forced describing 3 C's and going backwards, I would then say enthalpy actually increases. You'd say to me, well, wait a second, that's not what it wants to do. You're right, that's not what it wants to do. But going from this side to this side, I would have gained heat. And what about entropy? The entropy here has actually decreased. Again, not what nature wants to do. Nature wants to unwind. Nature wants to go to the other side. But I'm forcing you to describe having going from products to reactants. The entropy, the amount of chaos, the amount of randomness in the system actually drops. Okay? So that's all fine and dandy. We just sort of assume for the rest of this chapter here, these are set up to be in equilibrium. Then we introduce our main concept here of Le Chatelier's principle. Make sure you're able to state Le Chatelier's principle. Couple key features. The system has to already be in equilibrium. Okay? If we're not at equilibrium yet here, don't even bother with Le Chatelier. What I do to the equilibrium, it's in this nice, happy, balanced state here. I poke at it. When I poke at it, I increase temperature, I decrease concentration, I change pressure, I do something to the equilibrium. What's going to happen in the system is nature is going to try, it's going to tend to counteract me, and the direction is always against me. So if I heat it up, nature wants to cool it down. Is it because nature likes things cold? No, it just doesn't like the fact that I've heated it up. If I cool things down, it'll want to heat it up. Nature's always fighting you. You can sort of memorize for yourself here. It's sort of like saying nature tries to undo what we do. Although if I ask you to state Le Chatelier, you want to sound a little bit more scientific than that. Okay? So here we sort of separated two features. We poke at it with our stress, and then we tracked how the equilibrium responds with the shift. This is how the equilibrium responds. Remember, the equilibrium does not have a mind of its own. It doesn't like, oh, you heat it up, oh, I want to cool it down. We saw that explaining in terms of rates here. Naturally, we either shift left or shift right. We're still stuck in the box, but we can actually shift to try to get rid of your change. So let's have a look here. Let's poke at it with the stress of temperature. Let's say the temperature is decreased. The reaction, the equilibrium system will gradually shift towards the side with more heat. So let's take here, let's say A as a gas plus heat in equilibrium with B. You have to remember that this system here, all the chemicals are sort of stuck in this box here. When you cool down the box, you cool down all the particles, everything cools down. So A slows down, B cools down. You can think of heat as a chemical, just for convenience here. The heat term is going to go down. Which way do I want to shift to so that I end up generating more heat? In this case here, you should be able to tell me, well, the heat has dropped. I want to preference the reverse reaction. The reverse reaction, sure, it's going to make B become more A, but it's going to spit off more heat term. It's going to try to bring up that heat a little bit. So as a consequence then, after the shift, you can just write the standard words here, the equilibrium shifts left, or you can say shifts to reactants. And because it shifts to reactants, we can say the A concentration is going to go up, the B concentration is going to go down. Now, temperature change was a really special one, where because the products in this case here, they went down one way, the A went up one way. Overall, when we define that KEQ later, KEQ here is a number used to describe equilibrium. KEQ is described by products over reactants. KEQ only changes with temperature. So we have a situation here where we have A and we have AB. So KEQ is supposed to be, I'm going to say for argument's sake here, they didn't give me my reaction. So let's say the reaction was A and B becomes AB. Right, so slightly different reaction from earlier. Products over reactants, AB divided by A and B. If I have numbers in the equilibrium constant, I would put them up into the powers. So products over reactants. If I have a situation where, in my situation, my products went down, my products go down, my numerator goes up, the only thing that can happen is the KEQ is actually going to go down. As you look at the other stresses here, it might cause the equilibrium to shift. It might cause the equilibrium to respond. All the numbers here are actually different, but somehow, if it's not a temperature change, somehow the ratio between products over reactants before and after is actually unchanged. So, back to my initial here. Let's do concentration as a change. Let's increase the concentration of A all of a sudden. A is going to suddenly jump up. Okay? I don't like the fact that suddenly A is so much. Again, I'm stuck in this box. How does equilibrium respond? Suddenly having more A particles, I preference the forward reaction. I allow more of these particles to collide, good energy, good geometry. The forward reaction is predominant over the reverse reaction. I'm going to steadily lose A. Well, again, here's this notion. Le Chatelier tries to get rid of our change. It doesn't completely get rid of it. So, looking at this graph here, you notice that the A value is actually higher than what it was to begin with. My AB, which is on the other side here, as I shift to the right would gain. That one more gradually shifts, it goes upwards. But again, because this is not a temperature change, the KEQ ratio before and after, the KEQ is unchanged. This products over reactant number is unchanged. Okay. How about pressure and volume? Again, pressure and volume, we're specifically looking at gas changes. Let's say I decrease the volume. If you suddenly drop the volume, I go from a big box to a small box. Because concentration is N over V, suddenly having a smaller box would make all the concentrations suddenly jump upwards. So you see that for my gases, all the concentrations here has suddenly jumped upwards. Then what's going to happen is, especially, let's say back to my Haber process, if I did have one side 4 moles and 2 moles, seeing as I have so little room here, I'll probably want to shift to save some space. I want to lower the overall pressure. Let's go to the side with fewer moles. Maybe in this case here, I have fewer moles of AB gas, so I'm going to shift towards producing more AB. I'm going to ditch the side that has 2A and B like that. Okay, so make sure you're able to do Le Chatelier. Make sure you're able to predict which side shifts left or shifts right. Catalyst here is another thing I can stress out the system with, but nicely here for a catalyst, it's super simple because a catalyst lowers the energy barrier both ways. It speeds up both, so therefore we can say no shift. Both rates are actually faster. I mentioned there's some sort of industrial processes here. We talked about the Haber process, a really inexpensive way making NH3. There's another way of also making cement from limestone. Limestone here is this chemical here, calcium carbonate, and we end up forming oxides. That's an ingredient in cement. Okay. I did mention here this KEQ. Really, you can just call this K if you like. K is just a comparison between products over reactants. If K is big, right, products over reactant, that ratio is big, it just means that I have more products at equilibrium, so therefore I can say in terminology, products are favored. Even though we're in this balanced state, even though macroscopically nothing is changing anymore, I happen to have more products at equilibrium. Because KEQ has to do with concentrations, KEQ would never drop into the negatives. If K is small, how small are we talking? If it's between 0 and 1, right? That one means reactants are favored. We're in this balanced state here. Forward rate equals reverse rate. Concentration stay constant in time. But we actually have a situation where reactants are actually favored. Which chemicals are not put into this KEQ expression? Be careful to ignore solids and pure liquids. These ones here, if you talk about a concentration of a solid or a concentration of pure liquid, the only L in the equation, that's sort of like talking about a density. Let's imagine having one solid, let's say 3 particles in a box. You can have more solid. Let's watch the terminology here. More solid, you're right, I have 2 boxes. But instead of my concentration being 3 over 1, I have more solid. I have 6 over 2 times the space. Well, that ratio is just going to be the same. We can have more solid or less solid, but the concentration, the density is actually the same concentration of solid. So because that concentration of solid number never changes, there's no point in actually putting this in the KEQ expression. Ignore any solid. Ignore a liquid if it's the only L in the equation. If I have multiple L's, I have to include all of them. And we already saw that. Let's just do an expression here. Let's say AL and 2B solid becomes 3C as a liquid. When I'm writing the KEQ expression, I'm going to write it out with the chemical formula, so products over reactants. In this case here, solids are ignored. Don't worry about that. Liquids, I would usually ignore it, but because I have 2 liquids, they can actually dilute each other. So I actually need to include both. The numbers go up into the powers. C cubed times A. It would have actually been B squared, but I would have absorbed the B squared into the KEQ term. Okay, So that's what this KEQ number tells you. If this number is big, products are favored. If the number is small, reactants are favored. Okay. Concentration, pressure, and surface area, all of those may stress the system. All of those may cause differences, equilibrium would respond left, shift right, and things like that. But this KEQ doesn't change unless it's a temperature change. Okay. Keep that feature in mind. They always like testing you that. Okay. We're always going to assume that we're at 25 degrees. We can actually predict. Let's say this reaction here was actually exothermic. Let's say I actually increase the temperature. Okay. So as I increase temperature, the heat term goes up. I want to shift away from it. We know I'm going to lose C, my A and my B, even though B is a solid number here. Both of these concentrations are relatively going to increase. Well, what would happen if my KEQ is going to lose products and actually increase reactants? This fraction is going to get tinier. My KEQ is actually going to decrease. So for an exothermic reaction, you don't need to memorize it, but for an exothermic reaction, the hotter it is, the KEQ is actually going to get smaller and smaller, the more reactants are actually favored. Then towards the end of this chapter here, we started doing this with the ICE table. And ICE table uses as its heading the equilibrium system. It would be nice if they gave me the values at equilibrium. If I know, oh, we're at equilibrium already, here are all the numbers, here are all the amounts, I can find KEQ, I can use these numbers right away. Normally, however, we would have a container, and I would put in, let's say I just put in ammonia. Okay, so that would be in the initial row. I'm definitely not at equilibrium yet because I only have the reactant side. So if I just have ammonia, I might have this number here. What's implied here, I actually have 0 N2 and 0 H2. Now this question here can be worded a couple different ways. They can give you one of these amounts at equilibrium. They can say, yeah, you put in ammonia at the beginning, and at the end, once I reach equilibrium, I actually know the hydrogen is actually 30. If you know that number, then you can track the change line. I can't drop any lower than 0, so this is plus. N2 is also on the reactant side here, so this is also plus. The change line, because it's based on the reaction, the change line has to follow the mole ratio. So if you happen to know one of these numbers, it's a 1:3 ratio, this goes up by 1, this one has to drop by 20, we're done. And then we have these numbers. Whenever you have expressions for equilibrium, you're ready to sub it directly into the KEQ expression. In this case here, ammonia squared divided by N2 and H2 cubed. Most of this chapter here had dealt with gases, so that way we didn't have to ignore solids and liquids, things like that, but we can actually punch any of these equilibriums directly into the KEQ. Sometimes you're not given the change line, so let's just hint at what happens here. N2, 3H2, equilibrium with 2NH3. Maybe I had my ICE table, I had 0, 0, and I had maybe a Y amount there. Maybe I just put an amount, let's say I have 40. Well, I know which side is plus, right? I can't drop any lower than 0. This side has to be minus. If I don't know anything about the equilibrium line, I'm going to use an X. This is going to gain by 3. The change line follows the mole ratio, gain by 3x. This drops by 2x. If you have the I and the C line, you just do the math. What's 0 plus x? Well, x. 0 plus 3x? Well, 3x. What's 40 minus 2x? No clue what x is, but 40 minus 2x would be the expression. Again, we're ready to use the rest of the information and solve our way through for KEQ. There was one situation where this one was obvious because these sides were 0. Let's do the one last setup here. N2 and 3H2, they're going to choose numbers really nicely that you don't have to use a quadratic equation. But let's have a look here. We have, what if we have, I put in 10 N2, I put in 20 H2, I put in 30 NH3. The initial amounts are totally up to me. This time, I'm not sure which side is plus or which side is minus. What we're going to do is we're going to test the KEQ. The test KEQ is going to be a trial value. Trial value is basically, let's try to do a products over reactants right now, given the concentration as I have, depending on what number it is right now. Let me just punch through. Based on my numbers, I have 30 squared divided by, we had 10 times 20 cubed, like that. I'm going to type it in here. 30 squared divided by 10 divided by 20 cubed gives me 0.01125. So right now, my products over reactant number is 0.01125. Let's say the KEQ is supposed to be 5 at our temperature. Well, I notice my Q value is not big enough. Since Q is going to be products over reactants, for my Q value to climb up and get closer and closer to KEQ, I need to increase the products. So therefore, my reaction would have to shift right, positive, minus, minus. What if my Q value was actually bigger? What if my Q value, when I calculated it, what if it were like 20? Well, my value, my current product over reactant ratio happens to be a little bit too big. What I would do then is I would want to drop the 20. I want systems to naturally approach equilibrium. I want to drop my ratio. For this fraction to drop, I would need to lose products, gain reactants. So therefore, my equilibrium, or reaction, my reaction ends up shifting left. Okay? So sometimes when it's not clear which side is plus, which side is minus, you just test out what is my current equilibrium constant. We call it a trial value. And then we compare. If we are at KEQ, we're already at equilibrium. If I'm off KEQ, do I need to get smaller, shift left, or do I need to get bigger, shift right, in order to get to KEQ? Okay. So have a look at some of those problems and let me know if you have any problems. Thanks, guys.